Welcome everyone to today's presentation, where we will be introducing Realtek's microcontroller platform. The outline of this report is as follows, and it is mainly divided into the following sections for introduction. First is the overview section of this report, followed by the debugging methods provided in the SDK, then the algorithms supported, and finally some methods for using memory. Let's first take an overview of what is available. First is the debug module, which includes a trace API for log printing, a CPU monitor for a specified address range, and the ability to record logs to flash memory. Additionally, there is HAL debug, providing debugging log for common scenarios, and an interactive window console. Next is the crypto module, which includes support for some common cryptographic algorithms and adaptation for the Mbed TLS software library. Lastly, the memory module covers flash access, an easy-to-use flash transfer layer, a fuse for boot configuration, and management of RAM configuration and distribution sections. These functions provide comprehensive support for system debugging, encryption, and memory management. Start by introducing the debugging-related content. Printing logs is the most common operation. Currently, the supported log method involves directly transmitting the address of the string and parameters for assembly on the tool side. This approach saves MCU time and allows for the output of logs with higher bandwidth. Currently, for log levels are supported, and you can independently toggle the output of logs for any module and level. Error represents the most critical logs and will have 3 exclamation marks added to the string when displayed. Warning indicates a warning, meaning an anomaly has occurred, but the program can continue to execute. Info provides important notifications. Trace represents the execution trace. The format for writing the print function is shown below, and the log tool will print richer string information correspondingly. It is important to note that the first 2 positions, namely the serial number and timestamp, are added by the log tool when it receives the log. Additional information, such as subsequent serial numbers and timestamps, is generated on the SoC side during the packet assembly. Because the package is placed into a log buffer and only printed when there is idle transmission space or enough logs have accumulated, if precise observation of the execution interval between logs is required, it is recommended to refer to the SoC timestamps. The precision is in milliseconds. 1. Significant reduction in SoC CPU load. By delegating computationally intensive translation tasks, e.g., hex to string, to a PC, the SoC's CPU is freed from resource-heavy operations. This allows the SoC to prioritize time-critical tasks, e.g., sensor data processing, real-time control, and avoid performance bottlenecks. 2. Optimized serial communication bandwidth. Transmitting only encoded text instead of raw data or intermediate computation steps minimizes data traffic over the serial interface. Bandwidth savings reduces latency and congestion risks, ensuring reliable communication for applications like industrial automation or edge device networks. 3. Leveraging PC hardware capabilities. PCs typically have far greater computational power and memory resources compared to embedded SoCs, enabling faster and more complex translations without compromising the embedded system's stability. Scenario problem. In some cases, connecting to the log pin is impossible, breaking the normal log storage process. This makes it hard to get important data for system monitoring. Solution. The log-to-flash function stores logs in the flash. When a system crash happens, dumping the flash logs helps diagnose faults. How it works. It reuses the log printing API and creates a priority 1 task. This task runs when the system is idle to write logs to the flash, keeping app operations stable. The debug monitor is a feature provided by the ARM core, which allows for monitoring the bus behavior on the MCU. If a corresponding operation, such as read, write, or execute, is triggered in a specified address range, an interrupt is immediately generated, and the terminal execution function can be customized by the user. In some scenarios, such as discovering that a particular address has been incorrectly written, you can consider using the debug monitor for configuration. However, it is important to note that this feature can only monitor the behavior of the MCU and cannot detect incorrect writes by other masters. Provide common information that needs to be printed regularly. For example, regularly check the CPU loading, regularly check the heap usage, regularly check the cache hit rate, and regularly check the execution time percentage of each task. Universality and scalability. Console offers a versatile CLI, cross-platform compatible. It follows a standard format. Devs can easily add custom CMDS for seamless system expansion with few framework changes. Advantages in multiple scenarios. In debugging, devs use console CMDS to check vars and find errors, shortening debug time. In authentication, it validates user identities and perms for security. In auto testing, it interfaces with scripts for efficient test execution and result retrieval. Flexibility in mode switching. Console has string and binary modes. String mode, with human-readable syntax, is intuitive for beginners and basic tasks. Binary mode, post-parser registration, has high execution efficiency for high performance and large data volume scenarios. Then introduce the currently supported security-related algorithms. First, let's introduce AES, the Advanced Encryption Standard. This is a widely used symmetric encryption method, renowned for its robustness and efficiency. AES secures data by using a key for encryption, ensuring that only those with the correct key can decrypt and access the information. Our SDK supports AES key lengths of 128, 192, and 256 bits, allowing it to adapt to different security needs. The AES implementation in our SDK is performance optimized, suitable for both software and hardware environments, and comes with easy-to-use APIs and documentation. Next, we'll introduce SHA-256, an important member of the secure hash algorithm family, which is crucial for data integrity and verification. This hash function transforms data into a fixed 256-bit hash value, serving as a digital fingerprint of the original input. SHA-256 is collision-resistant, making it highly reliable for applications such as password hashing, digital signatures, and blockchain technology. Our SDK offers efficient and secure implementations to ensure quick and reliable hashing operations. The software library mbed-TLS provided by ARM officially has been adapted. According to the IP support of the IC, hardware acceleration has been implemented for some algorithms. Meanwhile, in scenarios where large global or local variables were previously used, heap memory allocation has been adopted instead. Additionally, thread safety has also been configured. Finally, introduce the memory-related content. Avoid erasure interference and ensure XIP operation in embedded systems. The erasure of flash memory often interferes with the XIP function. However, the rational implementation of flash technology can effectively circumvent this problem, ensuring the continuous operation of XIP and reducing the risk of performance degradation caused by timing issues. Enhance resource utilization and free up memory resources by applying this optimization strategy. More code can be executed directly from flash in XIP mode. This greatly improves the utilization efficiency of system resources, reduces the load on RAM, decreases the frequency of code loading, significantly enhances the system operation efficiency, and frees up more memory resources to guarantee the overall performance. Typically, the erase time for NOR flash is around 45 milliseconds. However, when erasing the flash, reading from the flash is prohibited. If interrupts are disabled during this period while waiting for the flash erase to complete, it could impact the normal operation of certain functionalities. To address this issue, the current solution is as follows. Interrupts are only briefly disabled during SPIC driver operations, and remain enabled while waiting for the erase to complete. During this time, the system pulls the flash status register, and the current task will not continue execution. However, ISRs that do not operate on flash can be executed, as shown in case 1. If the interrupt service routine includes flash operations or is XIP, execute in place, a wrapper layer is added. If the interrupt is triggered, the service code checks the current flash status to determine if it is in the erase state. If so, it temporarily suspends the flash erase, interrupts the current flash operation, and then executes the user-registered function. Once the interrupt ends, it determines whether to return to the previous task and, if so, resumes the flash erase operation, as illustrated in case 2. If a switch occurs to another higher priority task, the interrupted state of the flash erase is maintained, allowing other tasks to run normally. If the system returns to the task originally executing the flash erase, the scheduler function will detect this and resume the flash erase operation, similar to case 3. Determining whether flash suspension is needed upon entering an interrupt is done by checking if the interrupt service routine's address is within the flash region. Adaptation to diverse storage media. FTL supports both NOR flash and NAND flash, adapting to storage media with different characteristics and ensuring the stable operation of the system in a diverse storage environment. Optimization of address management. FTL allows upper-layer applications to register custom logical address lengths, dynamically allocate addresses, achieve address decoupling between modules, enhance the flexibility and scalability of the system architecture, and facilitate the efficient operation of upper-layer applications. Strengthening of cache mechanism. A cache area is set up in the system memory to store frequently accessed data blocks and address mapping information. When an upper-layer application makes a request again, the result is obtained from the cache, reducing flash access. Optimization of garbage collection mechanism. When adapting to NOR and NAND flash, garbage collection is crucial. Optimize the algorithm to preferentially recycle blocks with a low proportion of valid data, and adopt multi-thread or asynchronous operations to avoid interfering with normal reading and writing. For example, when the valid data in a block is below the threshold, a background thread is started to migrate data and erase the block, ensuring smooth foreground reading and writing. There are two parts, the physical area and the logical area. In the eFuse, a single bit can only be updated from 1 to 0, and there is no erase operation. It is mainly used to store some important and fixed configuration information, such as UUID, security key, etc. An MPPG tool is provided for users to update some of the eFuse configurations. First, load the ROM default settings. Secondly, when the bootloader starts, it will check whether the content of the eFuse is valid. If the eFuse is valid, load the eFuse settings. If it is invalid, directly use the default initialization configuration information in the ROM. Then, modify the corresponding configuration information, such as the flash layout, according to the config file burned into the flash. Finally, the app can update some settings according to its own needs, such as the data RAM heap size. The allocation of RAM depends on the usage patterns of different apps. Applications need to configure this part by themselves according coding result. The RAM for applications is mainly divided into three categories: RAM code, global variables, and heap. The lengths of an app's RAM code and global size can be configured by the following two macros. If there is any remaining, it will be incorporated into the heap for the application to use. Thank you.